Hi everyone, my name's Tom Wagg. I'm a PhD student at the University of Washington, working with Mario Juric. And today I'm going to be talking to you about this hybrid solar system catalog that we've been creating. So thanks for having me. So let's get into it. Let's first tell you why we've made a hybrid catalog. So what is the motivation behind this? Well, most current predictions for any sort of solar system objects with LSST use a full simulated catalog of the whole solar system. And so what this means is it includes everything in the solar system, even subsets and populations that have already been detected. And so the problem with this is we're not accounting for prior detections. What we want to do is make predictions for LSST that can account for prior observations. We don't want to predict, we're going to find a bunch of large asteroids, and we're really just predicting the rediscovery of Ceres. So that's why. Let me tell you how we do it. So what we're essentially doing is merging these. So what we're taking are objects from MPC Orb, which are real detections, and we are replacing similar objects within S3M, which is from Grav et al. 2011. It's a simulated solar system catalog. And this similar part is key because we don't want to change the underlying distributions. And so what we do is take some things that are very similar, swap them out, and so you have real things with the same distribution as before. So the way this works is first we just bin the data in terms of absolute magnitude and treat them all separately. And then we just step through each MPC orb object and we say, okay, what are the nearest 100 neighbors using a KD tree, and those that haven't yet been replaced. And of those nearest 100 neighbors, which one has the closest velocity? Find that one and then swap it out. And there is then a small case where if there are no objects that are close enough that can be kind of allocated with this swapping, we just directly add the MPC orb object. So I can show you an example of this in 2D on the right. This is obviously not the 6 dimensions of position and velocity that would usually be there, but let's just take the leftmost blue circle here. So for matching this one, we'd then look for the nearest neighbors, which are these kind of diamonds, and the closest one is pretty easy. We can just say, okay, that's the closest one there. For the next circle across, again, closest diamond, that'll be just that one. Things get more complicated here. So the closest, the next blue circle, the closest diamond is just the one right next to it. But for the next circle, you can't really do this in parallel, you see, because now the closest diamond has already been allocated. And so what we actually need to do is pick that simulated object to replace. And the final case is just in this bottom right. Say you are far, far away from any other simulated object. Any simulated object, you just directly add the real observation. And so that's how we are merging these two catalogs. And now we can maybe look at how well we're doing. So let's assess how well we've done. And what I'm showing you here is a plot of a series of cumulative distribution functions of different parameters. So at the top, we've got the absolute magnitude of each of these objects, and then the next row are the positions, x, y, and z, and then the velocities, vx, vy, vz. And you can see most of the time, you're basically just looking at one line, which is a good sign. These CDFs line up very well. Maybe slightly off in the absolute magnitude, but this is a log scale as well, so that's very slight different. And so I can tell you that they are statistically indistinguishable. If we do a KS test, if we calculate the KL divergence, all of those values indicate that these you cannot say with any certainty that these are drawn from different distributions, which is great. And the only differences that you see, for instance, in this absolute magnitude panel here, are just from those direct additions. So when you didn't have a simulated object that was close, when you just directly added it, you see these slight differences. And we can look at this just a different way. This is a density distribution looking kind of down on the solar system in terms of x and y. And on the left, you've got the real detections from MPC Orb. And on the right, we've got the objects that we picked to kind of swap out. And you can see, well, spot the difference with the image. They are pretty much indistinguishable. And so we did a good job. The hybrid catalog is reproducing these distributions. And so about out of time, so I will just say thank you for listening. I've shown you this catalog that has simulated and real simulated objects and real detections. The distributions that we've got in this hybrid catalog are indistinguishable from the simulated one, and any of these this catalog can be used to make predictions for any sort of solar system objects if you'd like to. So look out for an example of its use when I predict what the NEOCP, the Near Earth Object Confirmation page, is going to look like during LSST. And if you want to check out my website, if you want to email me, or you want to just try out the code, all the links are there at the bottom. So yeah, thank you for listening.